Thank you.
Okay, thank you. So you can see here that my name is Zeljko Arbanas. I am professor at the University of Rijeka, Faculty of Civil Engineering in Croatia. And here I will present some results of our project related to landslide initiation in small-scale slopes exposed to artificial rain. But you will see in my presentation that this is just a part of our results, and I have to say that we have so many data, very valuable data about landslide initiation in small-scale landslide models. And if there is someone who wants to cooperate and to analyze this data with us, all are very, very welcome. So we conducted a 4-year research project, and the title of project was Physical Modeling of Landslide Remediation Construction Behavior under Static and Seismic Action. And this project was funded by Croatian Science Foundation, started in October 2018 and completed 2 years ago. And it was completely conducted at the Faculty of Civil Engineering, University of Rijeka. And the main aims of the project are modeling and behavior analysis of landslide remedial construction in physical models of scaled landslide in static, that mean rainfall-induced landslide, and seismic, or better to say, landslide conditions. And here you can see our schematic models. The upper one is a model that we use for rainfall-induced landslide models, and on the bottom you can see this model for earthquake-induced landslide. So at this full model on the top, we apply artificial rain by 3 sprinkler branches, and this is in this case it is possible to model different rainfall events until the landslide was activated in the slope. In the bottom, you can see that we have a platform. Also, we put this platform at the shaking tables. It is a pair of shaking tables, relatively very small, and we also apply different rainfall conditioning. It wasn't necessary to have rainfall and earthquake in the same moment, but it is very important to have moisture of the model that was relatively very close to the rainfall events that can be done in the moment of rainfall. Here you can see our real platform in our laboratory. It is 2.3 meters long, 1 meter wide, and we put inside about 30 centimeters of material, of slope material. Construction of slope material was in 5 layers of material compacted with laths under compaction method, and each layer was of about 6 centimeters. If we are talking about this smaller platform, it is only 1 meter by half meter by 15 centimeters, 12 to 15 centimeters of material depth, because we were limited with the capacity of platforms, shaking platforms that is of about 130 kilos. And it is a problem because we, in this case, had a very, very small slope model. And here you can see the main part of our investigation. You can see remedial measures that we used and that we applied in our platforms. From top to the bottom, we have firstly gravity wall, and on the left side, on the left column, you can see neutral condition of the platform, and on the right side, you can see end of the test. And in the second row, you can see gabion wall, and in the third row, you can see pilot wall. And we tested all this construction in different conditions. What was equipment that we used in this model? First, we have tensiometers that we put inside the slope, pore pressure transducers, strain gauges, accelerometers. Then we have rainfall simulator. As I said before, it was one sprinkler system, and it was constructed of 3 branches. You can see here 4 branches, but we use only 3 branches, one in the upper part of the model, one in the middle part, and one in the top of the model. And each, you can see here is this photo of the model in the laboratory prepared for testing, and here you can see nozzles at each branch. We had 4 different nozzles, 4 different intensities of rainfall. We also had high-speed cameras. You can see here. It is a pair of high-speed cameras that can use that we can take about 5,000 photos per second. But in case of this type of landslide, it is relatively slow landslide. We need, of course, very low frequency of taking photo. We also use terrestrial laser scanner at the start, at the end of the test, because we need about 20 minutes to capture the model with terrestrial laser scanner. And also we used infrared camera. It was used some tests, but we didn't have so good results using this. What are the conditions of the model? We use 3 different types of material: sandy material, 0 to 1 millimeters, then sandy material with 10% of kaolin, then sandy material with 15% of kaolin. And it's possible to use different slope inclination. We use 30, 35, and 40 degrees. And we also use different initial moisture, different rainfall intensity, and different rainfall events. And here you can see grain size distribution curves for all 3 materials. I put these 2 materials in red because in my presentation I will present results using this type of materials, and also all results are related to 35 degrees of slope inclination. You can see that we have very small differences in grain size distribution when we add 10 or 15% of kaolin. But for these materials, we have a completely different behavior of slope. So you can see that when we add 10 and 15% of kaolin, we after that can obtain cohesion from 3.9 to 4.4. kilopascal, and you can see that we have some very important factors like hydraulic conductivity different from initial basic material. Here in this table you can see all properties of this material that we used in the models. Here is also one interesting element. It is initial water content. We use 2, 5, and 8.1% of water. It was important because before we started to construct the slope, we used these materials and we put in proctor tests to obtain optimal moisture for optimal construction of the slope. And this is the main reason why we use different initial conditions. And I will talk in my presentation about these two materials, sand and mixture of sand with 15% of kaolin. And the most important part of small-scale modeling, landslide modeling, and of course, for any small-scale modeling, are similarity laws. So here is a very complicated situation to obtain similarity between a real landslide or real slope with this small-scale slope. And we can talk about three groups of similarities. First is geometric similarity, and then is kinematic similarity, and the third group is dynamic similarity. And when we consider what we can put in this group of similarities, here in geometric similarity, we have model images, slope inclination, grain size distribution, moisture content, volumetric characteristic. In kinematic similarity, we have sliding velocity, sliding acceleration, waterfall velocity, waterfall acceleration, rainfall intensity, infiltration, displacement. And in dynamic similarity, soil weight, strength parameters, soil suction, active forces, resistant forces. But we have impact between these groups, and some parts of geometric similarity have impacts to kinematic similarity and dynamic similarity. And we also have impact from some elements of kinematic similarity to dynamic similarity, like as you can see here, infiltration has impact to soil weight, to soil suction, to active forces, to resistant forces. And also inside this group, sliding velocity has impact to displacement, of course. Waterfall velocity have impact to displacement. And of course, we have opposite interaction, and so suction has an impact to waterfall velocity. Resisting force has an impact to displacement, and so on and so on. And of course, inside the group of dynamic similarity, we have also some impacts. And it is very complicated situation. If you change any part of the model, you can have so many impacts to some other similarity. And regarding this, we can conclude that landslide is a complex geomorphological process if considering all the factors that should be taken into account when modeling the real landslide. And it is clear that the landslide process is too complex for all elements to be covered by similarity laws to fully describe the mechanism, initiation, and run-off process of a landslide. So the simulation of a real landslide in a small-scale landslide model must be limited to the application of the most important elements affecting the landslide process, while all other elements should be adjusted just to imitate a real process of sliding. And of course, we cannot consider that all similarity laws we should take only the most important parts of the process and analyze results only for this. Here you can see application of rainfall, artificial rainfall to our two models. We can see that we have different intensity of 72.6 millimeters of sandy slope per hour and 22.3 millimeter per hour for sandy kaolin slope. It is to avoid surface outflow, and intensities were adjusted to infiltration capacity of the slope material. Infiltration capacity for both material are much higher, but if we would apply higher values of intensity, rainfall intensity, it is problem with erosion process with surface outflow. And here on this diagram, you can see the process that we have during artificial rainfall. Here you can see position of the first crack that occurred on the slope, and you can see that we started with intensity from the start to the one point, this point, and also this point in the second test, were the points when the toe of slope was submerged, and in this moment we exclude branch in the bottom of slope because it was not so important for other part of the process. And at the end of each process, each test, we open all nozzles and start to apply the maximal intensity of rainfall just to see what will be after that. And here you can see development of the process in the sandy slope. The first crack occurred after 62 minutes, and after 130 minutes, we had development of retrogressive landslide to the top of the slope. And here you can see on these photos the process of this development of landslide to the top of the slope. And here we can see the movie. It is the movie that covers about 3 hours of the process of sliding in the slope, and this movie was constructed from the stereo pair of cameras, and it enables us to reconstruct the process. Right again. You can see that the process was started in the moment when the water in the lower part of the slope was covered the material in the top. So this is the end of the process. And here we can see the process in the sandy kaolin slope, and the first crack occurred after 35 minutes, and development of the landslide was in the other 65 minutes to the 100 minutes to the top of the slope. The first crack occurred in the middle part of the slope, but without significant movements in the slope. And the groundwater reached the slope surface in the middle part. You can see here, forming small springs and surface flows, and also erosion process. And we can say that it is joint mechanism of sliding and surface erosion, started with relatively fast retrograde stability development up to the slope. And here you can see developing of on one slide to the top. Here you can see a location of our sensors. We use three contour profiles. One, the lower part, in the lower part of the slope, in the middle part of the slope, and the last one in the upper higher part of the slope. And we put sensors at different depths at 6, 12, 18, and 24 centimeters from the surface, zero material in the flow. And we measured volumetric water content with sensor TEROS 10, pore pressure with TEROS 31, negative pore pressure better cymatic suction with TEROS 21 and 31. And here we can see results of this first. In the first row we have result for the material, and it is real. And from this result we can identify volumetric water content in any moment of the test, and also for water pressure. It was a problem because when we started with first test, we didn't have sensors TEROS 31, and it was not possible to measure soil suction that we have in the second test. And here is the process explanation. In the sandy slope with relatively high hydraulic conductivity, the volumetric water content increased due to infiltration until saturation in the deepest part of the slope, forming the water table. When it is established, the flow down the slope started, causing rapid rise in the groundwater level in the lower part of the slope, and this led to decrease in the soil shear strength, with complete loss of the matrix action, failure, and further retrogressive landslide development to the top of the slope. In the slopes made of sand-kaolin mixture with significantly lower hydraulic conductivity, the process of saturation occurred firstly in the surface layer. That caused an increase of the weight of surface layers, causing cracks and shallow instabilities in the middle part of the slope without significant movements. The opening of the cracks allowed the water to penetrate in deeper layers and form saturated saturated zones in the slope. And in some isolated local zones near existing cracks, the groundwater level rises to the surface, causing springs, pools, and erosion process. And for conclusion, we can say that landslide modeling in small-scale slopes exposed to artificial rain in 1G conditions is a complex process which requires a good knowledge of the behavior of the built-up soil material. The relatively small variation in applied soil material can lead to completely different instability mechanism processes. The leading parameters that remain stability in small-scale slope models at low confining stresses in 1G conditions are matrix action and cohesion. Application of model results to real slopes is a very demanding process that should include numerous elements in geometric, kinematic, and dynamic similarity laws that are interconnected and mutually dependent. And at the end, I will present you just some photos when we use remedial measures and the slopes, just to see results of this, but without any numerical value explanation. You can see that we prepared this gravity wall using 3D printer, and it was in a scale 1 to 20 to some real gravity wall of 5 meters. We had excavation of foundation pit. Then we put wall behind it. We prepared geotextile to separate coarse material that we put behind the wall. Here you can see also sensors that we put in the wall, and we compacted this material and we prepared slope with this. You can see here that we have stairs in a slope that enable better stability of this, and here is slope prepared for test. And after that we applied rainfall. Here you can see at the moment when the toe was submerged with material, and when the started initial crack, it was in the upper part of the slope, but not in the middle part. Here you can see the end of the test, and from this picture you can see that the wall remained stable, but it was problem with some deformation. You can see it is not in a line. We have some movement here in the middle part of the slope, and also we have activation of the passive zone in the front of retaining wall foundation. Here is the preparation for gabion wall. You can see one element of our gabion wall. We had element 10 by 5 by 5 centimeters. Then we prepare foundation for this gabion wall, of course, a material. Then put some lines of gabion, or using rule for arrangement of gabion as we used in the real construction site. We also put some material, coarse material behind the wall. It is also separated from the floor material with the geotextile. Here you can see additional zone, preparation of stairs, and finally prepared model for testing. Then we applied rainfall, and here you can see some results. After that we have some small cracks here, but the main crack occurs also on the top of the slope. We also have the same problem with this material, because here occur some type of swing because of rise of groundwater in the surface layer of this silt, some coloring material, and here you can see results to the end of the test. And this is the third test with pile wall. We prepared the foundation beam. It is not real in the practice, but it wasn't possible to obtain good foundation for this. Then we put piles, also prepared with 3D printer. Then we put material behind and in front. Then we prepare some buttressing material in front of pile. It was also separated with the geotextile. Then we put prepared drains behind the wall construction. Then we put cut beam to connect all piles in one pile wall. And here you can see the model prepared for testing. Then we apply the rain, and here you can see development of landslide, but on the top of the slope, the pile wall remains stable to the end of the test. But when we apply high intensity, you can see that we have some erosion process, but without losing stability of pile. And this is the end of the process when we stop the difficult rainfall. And this is the end of my presentation. As I said before, results were obtained from the project funded by Croatian Science Foundation, and some papers related to this you can find on this address. If you want to contact, here is my email address, and on the picture here you can see our truck sunk in the liquefaction that we obtained in a dynamic model and put on the shaking table. So this is my presentation. Thank you.